in the last video, we figured out the formulas for the observed period and frequency for an observer sitting in the path of the source. So the source is moving towards the observer. So this is the example where the train is moving towards you, and you perceive the train's horn as having a higher pitch or a higher frequency. And we were able to do that by just kind of doing a thought experiment, saying, OK, my object starts here. After one period, a period is just a measure of time, but it's the measure of time over which the source emits a cycle. So it emits a cycle every period. But after one period, we said, OK, where is that first wave front, or that first pulse, or that first crest? And where is the source? Because only exactly one period has passed by, and the source will be ready to emit another crest or another cycle. So the distance between where the source is and that kind of the front of the crest, or that first crest, that is going to be the wavelength, because this next thing that it emits is going to be traveling at the exact same velocity, and they're just going to be separated by that distance, which we saw as this expression. We said, how long will it take it to travel that distance? Well, it's traveling at a speed of v sub w. That'll tell you what the observed period would be for this dude over here. We calculated right here. And then the observed frequency is just the inverse of that. Now let's think about the situation where the observer is over here. The observer is over here. So these equations, or these formulas that we came up right here, this is observer, or let me say source traveling in direction of observer. Source traveling in observer's direction. Now let's think about the opposite case, where the source is traveling away from the observer. And that's, in this case, the observer is that guy over there. Maybe I'll do it in a different color. He'll be blue. So this is the observer. So when we started off, our source was right here. After exactly one period from the source's point of view, that first crest emitted has traveled radially outward that far. This is the distance. The velocity of the wave times the amount of time that's passed, velocity times time, is going to give you a distance. And where the source of the wave will have traveled to the right exactly this distance. Its velocity times the amount of time that's gone by. Now, in the last video, we said, OK, this guy, that wave is just passing this guy. How long will it take for that pulse that's being emitted right then to also reach him? And then that tells us the period between two pulses, or between two crests. Now let's think about that exact same situation here. That first crest is just passing this guy. And a period of, or a t sub s, which is a period of the emitted wave, has just passed by. So this guy is just about to emit another wave. So that other wave is going to be right here. So what is the distance between the crest, or the cycle, or however you want to think about it, the pulse that is passing him by right now? What is the distance between that and the pulse, the front edge of that pulse that is being emitted right at that moment? Right at that moment. Well, it's going to be this radius, which is this value. It'll be v sub w times the period. That is that distance, plus the amount of distance that our source has traveled away from this guy. So plus v sub s times the period. So that's what this distance is. And this is how far apart this wave pulse is going to be from that one, or this crest is going to be from that one. So if he's seeing this first crest right now, right at this moment, how long will it take him to see the crest that's being emitted right now, that's this far away from him? Well, it's that far away from him. So let me write this down. So the amount of time it takes for him to see the next crest, or the same point in the next cycle, that's the period. That's the observed period. That's going to be equal to this distance, the velocity of the wave, times the period from the perspective of the source, plus the velocity of the source, because the source has gotten that much further away from him. Velocity of the source times the period of the source. So that's how far the next crest is. And then you divide it by the speed of the wave, by the speed of each of the crests, which is just the velocity of the wave. And we can just factor out the t sub s's here and say this is t sub s times v sub w, the velocity of the wave, plus the velocity of the source, divided by the velocity of the wave. So this will be a larger observed period than if this guy was stationary, and especially if the observer was in the path of the guy. And it makes sense, because every time this guy issues a cycle, he is moving a little bit further away. So every crest, or the same point in the cycle, is going to be further and further apart. So you're going to have longer wavelengths, longer periods. And if you want the observed frequency for that guy over there, I'll do it in the same color. The observed frequency for a guy where the source is traveling away from him is just the inverse of that. So 1 over the period, same argument we did there. 1 over the period from the point of view of the source is the frequency of the source. Let me color code it. That is, so 1 over t sub s is equal to the frequency of the source. This is the inverse of that. So I'm just taking 1 over everything here. So 1 over t sub s is the frequency of the source. And then we take the inverse of this over here. The velocity of the wave divided by the velocity of the wave plus the velocity of the source. So we're done, at least for the simple cases. Obviously, it becomes a little more interesting when someone isn't exactly in the direction of the source or exactly being moved away from. But these are kind of the two extreme cases. So this is the situation when it is moving away from you. And just to check our math and maybe make it a little bit concrete in relation to the video we did where we introduced the idea of the Doppler effect, let's actually apply those numbers. So in that video, 2 videos ago, we had a situation where the velocity of our source was 5 meters per second to the right, and the velocity of the wave was 10 meters per second outward, radially outward. And the period of our wave, I'll call it the period of our, let me do another color. The period of our, from the point of view of the source, was 1 second per cycle. And the frequency was just the inverse of that. So 1 cycle per second, or 1 hertz, which is just a cycle per second. So using those numbers, let's see if we get to the exact same answer we got in that first video where we first learned about the Doppler effect. So let's look at the frequency from the point of view of this gentleman right here. So the frequency of the source is going to be 1 cycle per second, 1 hertz. The velocity of the wave is 10 meters per second. Let me write this. 1 cycle per second. Velocity of the wave is 10 meters per second. The velocity of the wave is 10 meters per second. Minus the velocity of the source is 5 meters per second. So what's this going to be equal to? The observed frequency for this guy right there, the observed frequency for that guy right there is going to be 1 cycle per second times, you have 10 over 10 minus 5. And the meters per second cancel out. Meters per second in the numerator, meters per second in the denominator. So 10 divided by 10 minus 5, or 10 divided by 5, is going to be 2. So it's going to be 2 cycles per second. 2 cycles per second. And if you want the period, the observed period for this guy, it's going to be the inverse of that, or it's going to be 1/2 seconds per cycle. And this is exactly what we got in the previous video. Or actually, it was 2 videos ago. And what about the guy this guy is running away from? Well, do the exact same thing. You have 1 cycle per second, or 1 hertz. That's the emitted frequency from the point of view of the source, times the velocity of the wave, divided by the velocity of the wave plus the velocity of the source, because it's moving away from him. So it's 10 over 10 plus 5. That's 10 over 15. That is 2/3. So this is equal to 2/3. The units over here I'll cancel out. This was cycles per second. So 2/3 cycle per second, which confirms the numbers we got in that first video. So that should make us feel good. And it also makes a lot of sense. This guy is going to see the wave, each crest, more frequently. He's going to observe a higher frequency. If this is sound, a higher pitch. This guy, since each crest or the cycles are getting spread out, he's going to see them less frequently. And if this is sound, he's going to observe a lower pitch.